Okay. Well, today we're going to get going using some of this stuff, how to think about electricity, how to do some of the simple calculations that you'll need to do. Um, I thanks. Um, I wanted to get the test back today, but I was having some trouble with uploads for some reason with Fusion, so I guess that'll have to be tomorrow. Um, so I'll get the exams. I should get the exams back tomorrow. Um, and remember that tonight the STL files for your design projects are due. Um, Before we do anything else, does anyone happen to have any questions about that? Giving me those STL files. Remember to look at the assignment document. There's a few other things that are due too. And then we're going to do a quiz tomorrow um, based on the stuff that we're talking about today. So be sure you look back over this stuff, and um, it's these quizzes are never going to have any calculation. So the calculation stuff we're doing is not going to be on it. It's just going to be short answer questions about stuff that came up in class, just to get you to go back and refresh your memory on your notes. And today, what we're going to do um, is we're going to define some of the important quantities that we're going to need. We're going to define voltage. In parentheses, I'll say and electric potential, which is connected to voltage. Current, and resistance. Um, and we will talk about Ohm's law, which is the most important calculation that we're going to do with electricity. We're going to use an LED to see electricity. So we're going to set up a simple circuit with an LED in it. And then we're going to get into resistors in series and resistors in parallel. Okay, so that's what we're going to get into today. We're going to start wiring some things up, and we have some tools in this kit to help with wiring. To visualize electricity, there is a very effective way to think about it. You know, electricity is kind of electricity and magnetism work together, and there's sort of a tricky thing to have like a physical feel for because you can't really touch it or whatever, see it. But and so everything kind of has to be indirect, the way that we understand electricity. Um, but there is a very nice physical analogy as a way to think about it, and it pretty much is always correct. Um, so to visualize electricity, um, imagine it as liquid flowing through pipes. Um, and so the first, the simplest thing we're going to think about is here's our pipe, and we're going to care about what's happening. We're just sort of arbitrarily maybe just going to ask ourselves what's happening at this red cross section of the pipe. Okay, so you can think of liquid flowing through this pipe. This pipe has some thickness, and varying that thickness is going to be important to us. And this pipe, imagine it full of liquid. And there are different pressures on the two ends of the pipe. So let's say at this end we have a pressure P1. And at this end we have a pressure P2. Now pressure can do a lot of things, and it's not always a difference in pressure that matters. Sometimes the true pressure at a single point, in some ways it affects what's around it. But if you're trying to push liquid through a pipe in one direction or the other, the only thing that matters is the difference between these two pressures. So if this pressure P1 is greater than the pressure P2, then the liquid flows this direction. And if P1 is less than P2, then the flow is the opposite direction. And it doesn't matter if those pressures, atmospheric pressure in SI units in pascals is about 1 times 10 to the 5th pascals. So if you have a pressure of 2 pascals on the left side and 0 pascals on the right side, you'll get some motion of the water, the liquid in there, from the left to the right. And if the pressures are way, way higher, if the pressure on the left is 1 times 10 to the 6th pascals, and the pressure on the right is 1 times 10 to the 6th minus 2 pascals, 2 pascals less, that flow speed is going to happen exactly the same way as when it was 2 and 0. I mean, it would probably burst the pipe unless it's a very strong pipe. But if everything can withstand those pressures, all that matters is one pressure minus the other pressure. Okay. What else could affect the rate of flow? If the diameter of the pipe is reduced, the flow rate is reduced. And if the diameter of the pipe is increased, then the flow rate increases. At McDonald's, I don't know if they still do, but they used to give you these straws that were like twice as big around as the straws at other restaurants. They know they can get more soft drink flow into you, and then you buy more soft drinks if they have a bigger diameter pipe. So the first thing to notice is that flow is not caused by the individual pressures, P1 and P2. It's caused by the difference the pressure difference and you can think of that as, P1 minus P2 or P2 minus P1. All that would do is change the sign of the difference that you get. Okay, so all this stuff is pretty intuitive. Now we're going to relate that to the way electricity works. So here's the electrical analogy, or the electricity analogy. So here are the things that we've talked about. We've talked about the rate of flow of the liquid. We've talked about the individual pressures. We've talked about the difference in pressures. And we've talked about the thickness of the pipe. So the first electrical quantity I'm going to bring up is electric potential. And electric potential is equivalent to the individual pressures P1 and P2. We're going to do everything in standard international units, SI units. And so the SI units for electric potential are a common unit, volts. And we'll abbreviate it with a capital V. Okay, so if you think about that water flow analogy, you would expect, in order to get electricity moving, it's not going to be the individual electric potentials at a single point. It's going to be the difference in electric potentials from point to point. And so the next thing I'm going to talk about is voltage. And obviously that's an electrical quantity, a term that you've heard a lot. And voltage is the difference in electric potentials between 2 points. And when you think about the electricity analogy, think of voltage as being equivalent to the difference in, this is the analogy, so the difference in pressures between 2 points. So again, you could have, so imagine like an electrode sitting there coming out of the wall, and it says that the electric potential of this electrode is 50,000 volts. Okay, that sounds really bad, but before you know whether, probably just don't touch it, unless you have a good reason. But if you want to know if it's going to be dangerous or not, you have to know one other bit of information. you need to know what the electric potential is of the ground or whatever other thing you're touching. Because if the ground is roughly at 0 volts of electric potential and this is at 50,000, then you have a voltage, a difference in electric potential of 50,000 volts. And electricity is going to want really badly to flow from the high electric potential to the low electric potential. And so it's going to go through your body. And a lot of electricity is going to go through your body because that difference is so high. Okay. If it turns out the floor also has an electric potential of 50,000 volts, you would touch that and there would be nothing. There would be no motion of charges at all. Want to hear something crazy about pressure differences? Anybody here ever heard of professional saturation diving? So mostly in the North Sea, but in other parts too, it's very deep, and there's a lot of oil at the bottom, so there's a lot of reason to have oil rigs built up in the North Sea that drill into the ground and get this oil. But if you have machinery and stuff, you need to have power. And so how do you get, well, I guess there are two things going on. You need power going to the rigs, and then you need pipelines going from the rig to somewhere else to take the oil that you extract. And all things that are at the bottom of deep places still need maintenance. So what happens when a pipeline gets a leak or something happens with the electrical cables or something? Well, you have to send divers down there to fix it. There's no other way to do it most of the time. Okay, well, how do you send? So you picture scuba divers, but this is, say, 150 meters deep. Okay, and so if you're going to send a scuba diver down 150 meters, that's a gigantic difference in pressures from the top surface to down here. So you have to go down slowly and let all the cavities in your body equalize the pressure. And that's a little bit of a hassle. It would take a while to get down there. But the big hassle is once you've gotten down there at that super high pressure, the air that you breathe, if it's under that kind of pressure, is very quickly saturating your blood with molecules and atoms that are going to be dangerous when you return to the pressure. And in some cases, they're dangerous on their own and they have ways of dealing with that. But let's just say that it has to do with going back up to the surface. So if you send a scuba diver down there, which you plausibly could, you give them a big source of oxygen and they go down slowly, and slowly they equalize the pressure, and then they get down there and do all the welding they have to do. But in order to get the mostly nitrogen back to a safe level out of their blood, on their way back up, they would have to take so many stops to wait for this nitrogen to leave their blood that they would go down, do their work for however many hours you can work. Let's say they'd work for 8 hours, do a day of work. And then it would take them a week to go back up to the surface. Okay, so that is financially a problem, like paying someone for 8 hours and then they're getting 8 hours of work out of someone and paying them for 2 weeks. Okay, so what's the solution to this? The solution is, and it's the most amazing thing in the world, people started to realize, I think it was the US Navy that started experimenting with this in the late 60s. But okay, what if instead of having them go back up to the surface, we just let them spend a month at this insane pressure. Well, like maybe that would work, you know? I mean, most of these pressure things are pressure difference things, not absolute pressure things. Um, well, they can't stay in the water for a month, you know? But what if we sent down a pressurized thing? They rode down this pressurized thing that was pressurized to 150 meters, but they're in like a room eating their meals and whatever. They get down, they open the tank and get out into the same pressure, do their work in the water, then get back into their pressurized tank. We could leave it down there at the bottom of the ocean, but there's no reason we have to. It's easier to give them food and stuff if they're on the ship. So they take these, so these divers get into their insanely high pressure tubes, and 4 of them live down there together. Don't get distracted. This is so interesting, even if it doesn't seem like it. And so you have these 4 guys in this high pressure tube, and they get in after their day of work, and then the oil rig pulls them back up to the surface, but they're still at that insane pressure. So now they're in this just gigantic pressure vessel that, like, if it sprung a leak, everyone would be dead instantly. And that happened early on, that kind of thing, you know. They've pretty much ironed out the kinks and stuff by this point. But so people get into this tube on the ship, on the rig. It slowly pressurizes them up to this high pressure. It lowers them down to the bottom of the ocean. They get out into the same pressure, but now they're underwater. They do their welding for 8 hours. They get back into the tube. They pull the tube back up. They give them food and stuff. They can communicate with them like, oh, how was the day's work? Oh, good, you know, but they're in this high pressure tube, and they do that day after day for a month. I think a month is about the standard time that they do this work. And then at the end, you know, I said that the scuba divers would need 2 weeks to get back up to the surface. Well, now they take their 2 weeks, but they've gotten a month of work before they've had to do it. They take their 2 weeks to slowly return them to ship pressure, to air pressure. And then finally, after a month plus 2 weeks, they open the hatch, everyone walks out, goes back home. It's like if you Google most dangerous jobs, that'll be one of the ones that's listed, because there's all these things that can go wrong. And apparently it causes some joint problems and possibly some memory problems and stuff long term or whatever. But yeah, then they just go back to their life, and these people get paid a ton of money, and they work a pretty small fraction of the year. You know, they're just recuperating a lot of the time, but they're just up at home doing whatever. And then when it's time to work again, they fly to wherever they're going, and they go through that whole process again. But I just think it's so interesting. Like, and it's kind of like it kind of brings up the difference between pressure difference and pressure, because when they're down there, they're really functioning pretty normally. There's nothing that you really have to do differently once you're at this high pressure. All of the cavities in your body are at that same high pressure. And so any of the things that would be caused by pressure differences are not an issue. You're just, everything's at a higher pressure, you know. And the funniest thing about all of this is, like, this is the, like, most dangerous, macho, toughest job in the world or whatever, you know. But the nitrogen in normal air would cause mental problems that it would kill you. And so they can't breathe normal air. But helium, if you replace the nitrogen in the air with helium, it turns out that it works fine. It doesn't cause these problems when it enters your blood and enters your brain. And so these people are, air is about I think about 80% nitrogen and 20% oxygen, basically. So instead, they switch over to it's a slightly different ratio, but basically mostly helium and then a little bit of oxygen. Um, but so when you hear these guys talking from the bottom of the ocean, they sound like Mickey Mouse. Like they have that thing with their voices, because they're breathing helium nonstop. And in fact, they have so much helium that it's hard to even understand what they're saying. And so they talk into these decoders that sort of like slow down their voice a little bit so you can hear what they're talking about. But the whole thing just sounds impossible. But they do it, and that's still how it's done, and it's been done that way since 1970 or something. Um, and okay, I'm not going to get into the accidents, but the early on years, the accidents that happened uh, were unbelievable, and it's just because of the difference in pressure between what's inside that pressurized tank and atmospheric pressure on the ship. Like there's this, like if you're giving food to people or whatever, you put the food in an intermediate section, you seal that off, then you pressurize that intermediate area, then you open the inside thing and they can take it. But before there were all the very careful redundant checks and everything to make sure that that worked. Like there's one famous one where uh, they thought it was sealed and pressurized and it wasn't, and somebody opened the hatch and everybody was just instantly gone. Like there were just basically like there was goo. That's all that there was. There were no people. There were suits and just globules of goo everywhere. So
does that affect the temperature of the food too?
yes, that's a really good question. So temperature is a big thing too, because if you uh, if you take this much volume of any gas and compress it down a lot, the temperature goes up a lot. That's actually the principle on which air conditioners and heat pumps work. And so yes, they have to do all that stuff, and all the calculations were done, and they've ironed out the kinks now and stuff. But that's another source of danger is there can be big thermal changes if if the um, if the heating and cooling systems fail, and a lot of the major accidents have come that way too. Yeah, exactly. Okay, what are we talking about? Electricity? If you want to know more about saturation diving, go to your local library. Um, okay, so voltage is the equivalent of the difference in pressures. Um, and really, what it is the difference in electric potentials. Um, one thing that we're going to try to emphasize is it always matters. So the difference in electric potentials matters, but you also have to keep track of which electric potential is bigger than the other one. That's going to determine the direction of electricity flow. Um, so which side, or let's say which point, you always take a voltage between 2 points. So which point has, hold on, my computer. Okay, which point has the higher electric potential is important. And in electricity, that's called the polarity. So if you know which like when you look at a battery, one terminal has a positive and one terminal has a negative. That's the polarity of the voltage of the battery. Um, and the thing I want you to always remind yourself as you're dealing with voltage early on until this is sort of ingrained is that voltage is always measured between 2 points. Electric potential, on the other hand, is measured at 1 point. Uh, and I didn't give the units. I guess I'll do that. But if you subtract two things with the same units, if you have 7 meters minus 3 meters, the answer is in the same units, 4 meters. And so that's how this works. And you would imagine that the units for voltage would be volts. And again, it's denoted with a capital V. Okay, so I want you to think of voltage as kind of the what makes electricity flow, but it's really not the electricity itself. What I want you to think of as the electricity itself is the current. Um, and so this is equivalent to the rate of liquid flow. So if you have a high current, you have a lot of electricity flowing. A low current, you have not much electricity flowing. And if you're trying to think about, how about the danger of an electrical shock or something, what determines that is the current. Okay. The voltage determines it indirectly because the voltage, if you think of that as the pressures that are going to force fluid from one side to the other, voltage is what makes that current flow, but it's actually the current that causes the shock if it's a person, or makes the electrical device run if it's what we're going to be trying to do is make electrical devices function. So current always flows from the higher electric potential to the lower. In other words, from the positive to the negative in terms of polarity. The SI units are amps, It's really amperes, named after some old French guy named Ampere, but everybody says amps. And it's denoted with a capital A. And current has an amplitude an amount and a direction. And we're going to always want to keep track of the direction of that current. And I'm not going to put this in the notes, but I do want to just mention this. When people were first studying electricity and figuring out how electricity worked, they didn't know what it was physically that actually caused electricity to flow. Well, they had two possibilities in terms of like thinking about polarity. It could either be positive charged things moving around, or it could be negative charged things moving around. They had to guess one or the other. They guessed positive. They guessed wrong. It's really electrons, it turns out, you know. And so there's a little bit of a source of confusion. If you're really following what's happening physically as electricity flows, it's really negative charges that move, and it would be like sort of a negative current that's happening. But it works exactly the same way. All the math works the same way, to just think about positive charges moving the opposite direction. And so that's what we're going to do. And that's thinking about the motion of positive charge, or thinking about positive current, the direction of positive current is called conventional current. Later on, if you're thinking about quantum mechanics and things, you can't avoid the fact anymore that you have to consider what electrons are doing. And then you have to make this distinction between conventional current and the true flow of the true motion of electrons. But for us, everything that we're going to do, we're going to think in terms of conventional current. Okay. Okay, so what I want you to keep in mind when you think about current, notice that current, this is the amount of electricity flow. And so this is what we're going to need to control to power devices. So we need this to be the proper amount and direction for a given device. There are some devices we'll use where it'll work kind of the same way no matter which direction current is flowing, but most of the time you'll need to control, you'll need to be aware of what direction electricity is flowing. And then the last one that we're going to talk about today is resistance. And in the fluid flow analogy, this is equivalent to the narrowness of the pipe. Okay, so if you think about liquid in a pipe, so say you're going to have a pipe and you already know what the pressures are at the two ends of the pipe. by changing the thickness of the pipe, you can change how much liquid is flowing from one side to the other. That's the McDonald's straw thing. So if you make the pipe really wide gauge, then for a given difference in pressures, you get a ton of electricity flow. If you make that pipe really narrow, even if those pressures are the same, you don't get as much fluid flowing through the pipe. And it works the same way with resistance. For a given amount of voltage, if you have a lot of resistance in your wire, a lot of resistors laid out along your wire, then the current flow is small. If you have very low resistance, then you have a big current flow. And so that gets to the importance of superconductors, because for a given amount of voltage, if you have almost zero resistance, you can get this huge flow of current if you have almost zero resistance. The SI units for resistance are ohms. That's another guy's name, and it's denoted with a capital Greek omega. And so the way it works, I guess I was just describing this, but for a given voltage, if you increase the resistance, then the current is reduced. And if you decrease the resistance, the current is increased. Well, that's going to be a really important thing for us. We have we have this cabinet over here that has resistors that have all sorts of different values of resistance. And when we power devices, we're going to want to have a certain amount of current going to the device. Well, we don't really have infinite control over what the voltage is that we use. But for a given voltage, we can increase or decrease the current flow just by putting resistors in our circuit. Okay, so we're going to use this fact pretty often. And mathematically, the way we're going to use this is, so this is all of the things that we need right now for the fluid flow analogy. Now, to put those together, the mathematical tool we're going to use is called Ohm's law. And Ohm's law relates the current the voltage and the resistance in a resistive element. So that could be a wire or it could be a resistor. And just for getting used to talking about this stuff, when we talk about current in a device, we're going to talk about the current through the device. When we talk about the voltage, remember, voltage has to deal with two different points. So when we talk about the voltage of a device, we're talking about the voltage between one terminal and the other terminal. And we will refer to this as the voltage across the device. And then it's a resistive element, and we'll talk about the resistance of the resistance element. And so what Ohm's law says is for a resistive element, like a resistor, the voltage across the device is equal to the current through the device times the resistance of the device. So that mathematical equation is always going to hold, where V is the voltage across the resistor, I is the current through the resistor, and R is the resistance of the resistor. Okay. Anybody have any questions so far?
Yeah.
Yeah.
So voltage measured from 2 points, it's how much potential energy there is. How do you measure that when something's running? Like, I mean, I know how you can, but how does that work when you?
Even when something's running, the you can measure the. I mean, sometimes making something run changes the voltage a little bit, but there is still a difference in electric potential even when something's running. And so, I mean, we'll use multimeters to measure this stuff. But you know, if you had a motor or something, you could put one terminal of a multimeter on one terminal of the motor, one on the other, and this multimeter would still just tell you there's a voltage between them.
Yeah. So is that just measuring how much is left over that could be still used?
What it's really telling you is what electric potential difference was required to force the amount of current through the device. And different devices have different needs for that. So like when we make a circuit with an LED, the LED is going to need something like somewhere around 3 volts, you know. And so if you put your multimeter terminals on the two sides of the LED, it would say 3 volts, and that's just saying that's how much electric potential difference was required to, you know, light this thing up. Speaking of that, one thing we're going to have to deal with when you're doing your robotics stuff is like a battery. You know, we have this box of 9-volt batteries, and it's not exactly 9 volts, but it's like right now, if you measured the voltage between the two terminals, it would say somewhere around 9 volts. But if you start asking that to produce current, that voltage will drop. And the biggest difference between a big, powerful battery and a small battery like this actually is not the voltage. The biggest difference is how much current it can provide without the voltage dropping very much. So, like, for example, a car battery is 24 volts, 24, right? 24. 12. Okay. A car battery. So a car battery is only 12 volts. It's this huge thing. You'd think, okay, it must be like 200 volts or something. But it's not the voltage. The voltage isn't the reason it's so big. The reason it's so big is that it needs to be able to produce a ton of current and still maintain that voltage. you could wire, if you wire two 9-volt batteries together in series, that's 18 volts. Like that is more voltage than a car battery, which seems kind of amazing. The problem is if you asked it to produce the amount of current you need to um, to make a, start a car, it wouldn't even come close to being able to provide that amount of current. And so anyways, that's called the internal resistance of batteries, and we'll talk about that. So it's not just, when we use batteries, it's not just the unloaded voltage of the battery that matters. It's the voltage it can provide while it's, running your circuit.
What kind of things like high voltage, low amperage batteries? What kind of stuff is that used for?
High voltage, low amperage. Well, anything that just doesn't, like basically the smaller the device, the less current you need.
Yeah.
So I can't think of anything off the top of my head that requires a really high voltage. But like the devices that we're going to use for the robotics are pretty much all going to require 5 volts. And they're just built that way because 5 volts, we'll see, is something that we have a lot of access to. So yeah, nothing jumps out at me that requires a high voltage and a low current. But we will have, there are some devices in those cabinets that will require more voltage than one battery will provide, but not much current. And so then we'll just wire up 2 batteries in series, and it'll meet that voltage requirement. And since the current requirement is low, it'll be fine. Yeah. Anybody have any other questions about any of these concepts so far? Okay, so if you're thinking about the fluid flow analogy, what is the name of the electrical quantity that's equivalent to the pressure at a single point? So I'm just trying to start the process of getting this to stick in your brains, Electric potential, that's right. So that's like the pressure at a single point. So you have electric potential at a single point in a circuit. If you take the difference between 2 electric potentials at 2 different points, what's the name for that? That's the voltage. Yep. And the amount of electricity that's flowing through a point in a circuit, what's the name for that? That's the current. And then, well, the other one is resistance. I don't know how to say that other than resistance, but okay. So now we're going to think about our first simple circuit. So the first example here, and I'm just going to draw a picture of this circuit. So let's say that we have a 9-volt battery. So this is 9 volts, and we have the positive terminal here and the negative terminal here. And let's say we connect a wire from the positive terminal to a resistor, and the resistors look like this. And you have a bunch of those in your kits. It's like a little thing shaped like this that has 3 or 4 colored bars on it. And then we go from the other terminal of the resistor to the negative terminal of the battery. And let's say that we're using a resistor of 1,000 ohms. And we want to know how much current and what direction is flowing through that resistor. Okay, well, when we do these calculations, we're always going to assume that wires, if all you have is a wire and you don't have any devices on it, that wire has zero resistance. And the effect of that is that every point on a connected wire so let's say every point on a wire that's connected has the same electric potential. So if you can get from one point to another point and travel through nothing but wire, all of that has the same electric potential. So all of this has the same electric potential, and all of this has the same electric potential. And so all of those points with the same electric potential are called nodes, or a node. So all of this that's circled in red is a node, and all of this circled in green is a node. Okay, so what does that tell us about this circuit? Well, we know that there is a voltage, a difference in electric potential of 9 volts going from the positive to the negative terminal of the battery. Okay. And so then we don't care what the individual electric potential is. This could be 50,009 volts of electric potential, and this could be 50,000 volts of electric potential. All we know is that there's a difference of 9. Or this could be 9 and this could be 0. That's an easier way to think about it. Doesn't hurt anything to think about it that way. So since all of this circled in red has the same electric potential, we can also think of this as having an electric potential of 9 and this having an electric potential of 0 since it's connected to this one. Okay, so I'm going to start out by I guess I'll redraw this, make it a little cleaner. But what we've figured out now is the voltage across that resistor. This one is at +9, and this one is at 0. So the voltage across the resistor is 9 volts. And the polarity is shown. Okay, well, we know that the resistance is 1,000 ohms. And so now we can go to Ohm's law. and it says that, so V is equal to IR. I is the current. And so 9 volts is equal to the current that we're trying to find times 1,000 ohms. And so the current is equal to 9 divided by 1,000. And if you divide that out, you get 0.009 amps. The currents that we're going to deal with are pretty rarely going to get up close to 1 amp. There are some devices you'll use, well, they'll get up there, maybe a little above an amp. But for the most part, we're going to be dealing with very small currents. So a lot of times people, instead of using amps, use milliamps instead. So this is equal to 9 milliamps. And if I draw this resistor one more time, so here's what we've learned. We have a voltage of 9 volts with the polarity in this direction. And the current always flows from the positive to the negative, the high electric potential to the low. And so the current is in this direction, and we'll always indicate direction of current with an arrow. And it has a value of 0.009 amps. Okay, if we wanted to make a circuit that looked like this, you can imagine doing it with alligator clips on everything. But it gets or taping things or whatever with electrical tape, but it gets a little cumbersome. So we have something in the kit that is going to be really useful called a breadboard. And it looks like this. And there are little connections all over the place. And I'm going to first draw lines and then draw the little connections. And these go all the way down. And it doesn't show them on the breadboard. You don't see them as lines like this. What you see is dots, holes. But the idea is that anything that's on these lines that I've drawn on here is part of a node. Okay. So any wires that you connect to the lines that are drawn over here are part of the same node. And the defining property of a node is that everything on the node has the same electric potential. Okay, so if I wanted to make this circuit that I've drawn here using a breadboard, I could do something like this. So if this is my 9-volt battery, um, I could connect the positive of the battery to this, which I didn't make that very clear. So that's going to be, these vertical ones are called the power rails. The red one is what I'm connecting to my positive power. The black one I'm connecting to my negative power of my battery. It doesn't matter which one you connect. And then I can take my resistor and plug it in here, for example. And I'm going to go from the positive rail to the node that has this side of the resistor on it. And I'm going to go from the other terminal of the resistor to the negative power rail. And that breadboard will just hold all those connections in place. And now what I have is, it looks a little messy, but it's not physically messy, like trying to connect alligator clips, all these things. We're going from positive to this rail, which connects to here. So we're going positive to here. Then it's going through the resistor, because this doesn't connect to this except through the resistor. And then from the negative of the resistor to here. Okay, well, let's get out the breadboards and okay. It would be a pain if you had to draw a picture of your circuit every time you wanted to convey to someone else the circuit that you want, or to take notes on it. And so one thing we're going to use is schematic diagrams. So instead of drawing pictures of batteries and everything, we're just going to use accepted symbols for those things. So here are the symbols that we'll use. For a battery, we'll use a long line and a parallel short line. So this is the symbol for a battery. All of these you can turn sideways or at any angle. And the meaning of the long is this is the positive side, and the short is the negative side. Sometimes you'll also see it given as a series of long and short. So you'll see a battery given like this. I'm just going to use the 2, but and again, the side with the long line is the positive, and the side with the short line is the negative. And then for a resistor, you use 3 jagged peaks like that. Coming up pretty soon, we'll be using voltage sources other than batteries sometimes. And so if you have a voltage source that's not a battery, that symbol looks like this, just a empty circle with a line connected to it, and it'll tell you what the voltage is of that source. For us, it's going to be 5 volts. So that's a voltage source. And then we'll also use grounds when we have a voltage source like this. You might, if you think about it a little, you might think like, well, wait, how can that be a voltage source if voltage needs 2 points, 2 electric potentials to make any sense? And that's a very, that would be a very accurate concern to have. And so when you're using a voltage source, that's always in reference to some ground somewhere. And the symbol for a ground is like sort of a Christmas tree thing like this. And so if you have a circuit that has a voltage source and a ground in it, then that's enough information to figure out the voltages for the things. And then since we're about to do something with LEDs, I'll give you the one for the LED. So an LED, you have a triangle with a line in front of the sharp end. And then you have 2 arrows coming out of it that, indicate the light. So this is an LED, which stands for light emitting diode. A diode generally is something that only allows current to flow in one direction, not in the other direction. And so the meaning of this symbol is like current can flow along the arrow, but if you try to make current flow in the opposite direction, it hits that wall and it can't flow. I think that's the idea of that schematic. Okay, so if we put these together into a schematic diagram of the circuit that we just put together. So schematic diagram of the circuit above. We would have the battery down here. And in our case, that's 9 volts. So I'll write that. And then we have wires going like this to the resistor. And the resistor is 1,000 ohms. Okay. So let's do another example, this time with a diode. With a LED. And what we're going to do is we're going to have a battery connected to a resistor, connected to a diode, and we're going to use a 9-volt battery. We're going to use a 330 ohm resistor. And all of this should, if you wire it up correctly, the LED will light up. And by the way, this works exactly equivalently to this. So you could, right now we have the positive current flowing from the battery through the resistor, through the LED. We could also have it go from the battery through the LED and then through the resistor, and the behavior of the circuit is exactly the same. And if you think of a resistor as a narrowing of a pipe, it kind of makes intuitive sense why these two are the same. An amount of fluid can only flow through this whole circuit, and so if you slow down the flow of the fluid before you get here or after, either way, it has the effect of slowing fluid going through this whole pipe. Okay, and it behaves the same. Okay, so what I didn't tell you yet, and this is important, is I said that LEDs only allow current to flow in one direction. So how do you know which direction, when you look at the actual LED, how do you know which direction allows current and which one stops current? And there are two ways to do it. The better way to do it is if you look at the rim of the LED, if you look around that rim, you'll see that over one of the two terminals, the rim is flattened. It's like it's clipped off or sanded or something. It's not very obvious. You have to look pretty closely at it. But if you just rotate that around, you'll get to a point on the rim where it's flattened down. Do you see that yet? You see it? What are you looking? Okay, so yours does not have it. Use one of the little ones. Those will have it. Yeah, this is flat.
Okay,
You see that?
so that's not really cool.
So that is the positive, I believe. No, that is the negative. The flat is the negative. Also, if you look at the length of the legs, the positive is the longer leg. If you look at the lengths of the terminals, that is not always a very reliable thing, though. The reason it's better to go on the flat thing is that people using these circuits often clip the legs to make them the same length, and then you can't use that anymore. Okay, well, why don't you try to put together using the breadboard and everything? And the resistor, oh, we're using the 330 ohm resistor, so that's the orange, brown. See if you can put together a circuit that lights up this LED. And I'll do it, and you can come up look at mine if you have a question.